At 200 miles per hour, air is not empty space. It is a physical wall. When a carbon fiber structure slams into that wall, it experiences violent, invisible pressure that warps and distorts its shape. In Formula One, managing that pressure is strictly regulated. Aside from the drag reduction system, the DRS flop on the rear, the FIA rulebook mandates that every aerodynamic component must be rigidly secured and completely immobile. Moving bodywork is illegal. This creates a conflicting set of requirements. Teams need large wings to push the tires down into the asphalt for grip through high-speed corners. That on the long straightaways, those same wings act like parachutes, creating aerodynamic drag that bleeds away top speed. To ensure teams aren't using flexible materials to shed that drag, regulators pull the cars into stationary garages. They hang heavy 100-kilogram weights directly from the wings to measure downward deflection. Pass the static test and the car is legal to race. At the Azerbaijan Grand Prix in Baku, McLaren's rear wing passed those stationary park for me tests perfectly. The car was certified as entirely rigid. This diagram shows what happened on track. Aerodynamic load forced the rear wing backward. The carbon fiber passively deflected, opening the slot gap. Tilt in 17 degrees drops load from 75 to 63 kilograms, netting an extra 2.4 kilometers per hour. McLaren did not build a mechanical device, and they passed the mandatory weight checks. Instead, they recognized a gap between the limitations of a stationary garage test and the dynamic laws of high-speed physics. Exploiting this gap relies on aero-elasticity, how a structure behaves when inertia, elasticity, and fluid pressure collide. Static tests use dead weight pulling straight down, but real aerodynamic load acts like a shifting wave, pushing backward and upward. As a car accelerates toward 200 miles per hour, the center of pressure migrates toward the rear edge of the wing. Hanging weights on a stationary car simply cannot replicate that rearward migration. To use that shifting pressure, aerodynamicists utilize a highly sophisticated manufacturing technique called Aero-Elastic Tailoring. This shows the raw material before hardening. Carbon fiber's structural integrity and flexibility are dictated entirely by the precise directional alignment of these composite threads. Engineers align the weave to be incredibly stiff against direct vertical gravity, defeating the FIA's downward test. Yet this exact thread pattern remains intentionally vulnerable to torsional forces, rotating when hit by horizontal pressure. This photographic comparison displays the real-world application on a front wing. At low speeds, the multi-element wing maintains its steep angle, but subjected to high-speed torsional load, the upper flaps physically warp and flatten backward. By flattening out, the wing sheds significant aerodynamic drag, allowing the car to cut through the air faster on the straightaway. When the driver hits the brakes, wind pressure drops. The carbon fiber instantly snaps back to its rigid, high downforce shape to cut the corner. Through Aero-Elastic Tailoring, teams weave a seemingly solid composite material into a speed-activated moving part. It flexes exactly when they want it to, and goes rigid when the inspectors come looking. Closing this loophole presents a near-impossible logistical hurdle for regulators. The FIA cannot reasonably mandate teams place fully assembled, multi-million-dollar race cars into operational wind tunnels under locked parc fermé conditions every single weekend. Because inspectors must use stationary tools to hit a moving, high-speed target, the regulations are locked in a constant state of catch-up. To patch the leaks, the FIA issues strict mid-season technical directives, like the recent TD018. This cross-section highlights what TD018 banned: teams hiding levers and sliding components beneath rubber surfaces, allowing wing flaps to pivot while maintaining a smooth skin. But when regulators ban flap mechanisms, engineers search deeper, twisting the entire main plane itself to expand the gap. This computational fluid dynamics visualization displays why that tiny gap matters. As the lower main plane deforms, the colored velocity streamlines smooth out. The airflow reattaches and accelerates over the wing, altering the aerodynamic wake. In the realm of aero-elasticity, macro performance is born from micro adjustments. Just a few millimeters of calculated flex on the main plane reduces the car's overall drag coefficient, shaving critical tenths of a second off lap times. A structure's true nature is revealed only when it hits the air, proving that in the harness tiers of motorsport, even the most rigid rules eventually begin to bend.